All right, good morning. We are here. I can get the slide to come up now. And let me give the last couple of announcements just for the folks who aren't here yet. Okay. My office hours, I think I told you earlier, were somewhat screwy this week. They are a little bit, but I've gotten some things taken care of that will fix them a little bit. I had thought that I would have to leave to go to the Birmingham campus at 3:15 today, which is when most of my office hours are, 3:15 to 5:15. But my afternoon class yesterday finished early. They were giving reports. They finished early, gave them the test. We finished that early, so I was able to leave and take care of the stuff yesterday that I had planned to take care of today. So that was good news. So I will be here 3:15 to 5:15 this evening. However, I have at least one student said he's coming by for tutoring, but come on in. All students are available to come in during office hours, not just who I happen to be tutoring at the time. So if you do have any need for me this afternoon, I should be here 3:15 to at least 5:15. Because of that second mini-term class, this many papers got turned in yesterday. Okay, so I've got a lot of grading to do for the class as well as picking up all this stuff. Okay. And I gave a test yesterday morning, and I still have that many to grade from that test. So, but I've got to get these graded because tomorrow is the last day of class. I want to return all the papers to them, even the late stuff they were late turning in. So I probably will be here past 5:15, but I'll be here at least through 5:15. Then tomorrow, I do have problems with office hours because we are going on a field trip to Channel 13 Weather Center, and that means I have to go pick up the vehicle, and the only time I can do that is from my office hours, 10:45 until 12:30. Now, it won't take that long. Hopefully I can be over there by 11:15 and maybe back by 11:45. Certainly by 12, I hope, because I'd like to have time to eat a little bit of lunch before we go. So most of my office hours tomorrow is kind of shot, but I will be in there some, hopefully between 12 and 12:30. Then on Friday, usually I'm on the Birmingham campus, 7:45 to 1. This Friday I've got my annual physical, so that's going to be at 8 o'clock. I've got to be at the clinic at 7:45, so I won't be on Birmingham campus then. And hopefully it'll be done within an hour, so I'll be able to leave and hopefully get to Birmingham campus by 9:45, around there. Maybe 10 o'clock if there's delays or something. Maybe later, but hopefully earlier. All right, those are my issues for this week. Hopefully next week will be more normal, whatever that is. Any questions on anything we've done so far? By the way, I do have all the tests graded and papers that you turned in graded. And yeah, I do need to say this, so let me say this too. Everybody except one person has turned in something. You two have turned in papers, and 3 out of the 4 have turned in the first test, but I still have one person who has not turned in anything. Okay, now, why am I saying that? This is the end. This week ends the first mini-term. Next week starts the second mini-term, meaning midterm is sometime this weekend. Okay, and usually the week after midterm, they have a thing on the academic calendar. It says midterm progress reports due anytime that week, next week. Okay, and why am I saying this? Well, what they want on midterm progress reports are any students who have D's or F's at midterm. The 3 of you do not. You have all turned in something, so you're in good shape. One guy who's not here hasn't turned in anything yet. Hopefully he will, but I really need it in next week. Otherwise, if they do request those, then I have to say he's failing at midterm. So that is important. I'm saying this not just for you or for him, but also for any friends you might know or any other classes you're in. If you have work you haven't submitted, please get it in before next week, okay, or by next week sometime. All right, any other questions? All right, where we left off last time was on page 68, chapter 2, matrices, 2.3, inverse of a matrix. And here is a theorem. We got right up to this, but didn't have a chance to do it. We've hit it before. No, we haven't. Maybe not. We hit something pretty close to it, maybe in a discovery. Here we have the, whoops. Okay. Let me get my pen activated to the right color, but it's not doing anything. It's still not, there it comes. Okay. Let me also get the eraser. Okay. So here we have A and B are invertible matrices. Tell me what that means. Something that means. Something you know about those matrices without anything else being said. They're square matrices, of course. Okay? It also means, what about the determinant? We haven't talked that much about the determinants, but at least by 2 by 2s. What would that tell you if they were 2 by 2? Yes, the determinant is not 0. Okay? Another thing, if they're invertible, another word for that is non-singular. Okay. Several things we know just by knowing they're invertible matrices. They're of order n. Now, this thing about the determinant is still true. It can't be 0. You just don't know how to take a determinant anything larger than 2 by 2. But it's still true. Now, so if A and B are invertible matrices of order n, that implies that AB, the product of A times B, is also invertible. That's what this theorem is claiming. And if the AB is invertible, what is the inverse of AB? It says it's invertible. What is the inverse? Any guesses? So again, B inverse times A inverse. Exactly. Okay? So, we've seen that kind of pattern true in other circumstances, like transposes and things like this. Same thing here. All right? Now, so basically, these two things, number one, the product is invertible, and number two, that's the inverse. They're going to prove in one big thing, okay, that if you have a product, AB, okay, that's what we're doing. We're trying to show that's invertible and that this is the inverse, okay? Well, AB, if this is indeed the inverse, then AB times B inverse A inverse, we know what that's got to be, don't we? If that and that are inverses of each other, what's the product? The identity matrix. So let's see if that's at all true. The first thing we're going to do is fiddle around with parentheses. We're going to do A times B inverse times A inverse. Right? What's B times B inverse? Given that B is invertible. That's the identity matrix. So this is A times I, and by the way, that's IN if you want to be specific about it because it has to be order n, times A inverse. Okay? Well, guess what? A times the identity matrix is what? It's A. That's why it's called the identity matrix. So this is A times A inverse, but what is A times A inverse? It's the identity matrix. And sure enough, we've shown that the product of these two products gives you the identity matrix, so therefore these must be inverses of each other. And it's pretty easy to do it the other way too. Hopefully you see that. If you do B inverse times A inverse and multiply that by AB, guess what? These two form the identity matrix. These two form the B inverse. and these two form identity matrix. Okay, so yeah, same type proof. So yeah, that product, if we're given the A and B are invertible matrices of the same order in square matrices of the same size, then the product is doable. It has an inverse, and that is the inverse of it, and we've just shown it, given what we need. Make sense? All right. That theorem, 2.9, states that the inverse of a product of two invertible matrices is the product of their inverses taken in reverse order. Now that can be generalized to be any set of products of several invertible matrices. So if all these are invertible, I think I'll go to a clean page if I can find my cursor. If you have A1 times A2 times A3 times, well, wait, no comma, no comma, no comma, this thing is being so obstinate today. Okay, multiply those together n times. N matrix, all the same size, all square, and if they're all invertible, then the inverse would be what? You give me a guess. If we can extend the previous theorem, what would that product of n invertible matrices be? The inverse of that. A, n, A, n minus 1, A, n minus 2, dot, 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 down to A3. Oh, whoa, 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 you let me get away with that. These are all inverses of those matrices, but in reverse order. A2 inverse times A1 inverse. If those are invertible matrices, the product of all those matrices, if they're same size, same order, then, and the n here is a counter, it's not the order, then the product of all those would be the product of the inverses in reverse order. Okay? And you could check that by doing the same thing we did before, multiply, not with the inverse sign up there, multiply those by this, every pair in the middle form the identity matrix. Okay. It says, see example 4 in Appendix A. I'm sure y'all are going to rush to see that. Right. Good. Do it. So let's do example 7. And because we may take some more room, I will erase this ink and do this. So, it says find A, B inverse for these matrices. A is equal to 1, 3, 3, 1, 4, 3, 1, 3, 4. B, throw your book around, see if I care. 1, 2, 3, 1, 3, 3, and 2, 4, 3. All right. Now, there's two ways you could approach this. Okay? What would be those two ways? Find the inverse of each one, and then multiply them in reverse order. Okay. Now, what's the other way? Multiply them, and then take the inverse of that. Okay? Now, I know which one they want us to do. They want us to take the inverse of each one and then multiply them in reverse order. that is two inverse operations and one multiplication operation. Okay? Doing it the other way is one multiplication operation and one inverse operation. This is an easier way. Okay? But since they've done it the first way, the long way, let's us do it the other way and show it's the same. I know that's not what their intention was, but let's do it. So, first thing you do, what is AB? What size will it be? Or can you even multiply them? Sure you can, 3 by 3. Okay? Sock it to it. One plus 3 is 4, plus 6 is 10. Next, if you're doing the 1, 2, that would be 2 say again, plus 9 is 11, plus 12 is 23, right? All right, this high-level math is tough, isn't it? Okay. Now the 1, 3. 3. Say again. Plus 9 is 12. Plus 9 is 21. Okay. Feel like a dentist here. Okay. The 2, 1. That would be 1 plus 4 is 5. Plus 6 is 11. Next, 2, 2. 2 plus 12 is 14. Plus 12 is 26. Am I getting it right? Okay, just a couple of things. I put it on Screencast-O-Matic, which will be on whatever you call it, YouTube, sometime later today, but just in case you need to know it now. This is the end of the first mini-term. This week is, okay? Meaning sometime this weekend is the midterm. And sometime next week, we're supposed to, at least on the academic calendar it says, we're to do midterm progress reports. A lot of times they forget to open that because there are administrators who open it and they don't read the calendar, okay? If they open it, I have to report on anyone who has a D or F at midterm, okay? That means I need a grade for everybody sometime, either this week or next week. Please, get me something, either the paper or the first test, or both, or whatever. So please do that. Okay, let's do the 2, 3. What would that be? First entry, 3 plus 12 plus 9. 3 plus 12 is 15, plus 9 is? No, 24, isn't it? Yeah, 24. Sorry. Too much. 24, if I could write. All right, 3, 1. 1 plus 3 is Earth to class, come in please, okay. 1 plus 3 is 4 plus 8 is 12, right? Is it right? Okay. Then 3, 2. 2 plus 9 is 11 plus is 27. And lastly, 3 is 12 plus, yes, 24. All right, that was harder than I thought it would be, right? Okay. Now, how do we get the inverse of that? Okay, say again. Okay, I heard you say use the identity matrix. Is that, yeah. Okay. How do we use it? And there's a couple words for it. Augment or adjoin, both of those will work. The identity matrix to this one. That would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Now I'm beginning to see why maybe the other way was easier. Why? Really easy to do row reduction on those two because you got lots of little numbers in your first row.
So,
column.
What did you just do?
What's that?
What did you just do right now? You added 1, 0, 0, 0.
Okay, I couldn't hear.
I said, what did you just do to the?
Oh, okay. When we're trying to find the inverse of that product, first we did the product of those two, we got that. To find the inverse, you adjoin or augment the matrix you're interested in with the identity matrix.
Okay.
Then you do row reduction here, and what your answer is, if these all turn out to be an identity matrix, then what you have on the other side of your row reduction will be your inverse.
So it's like do what we was doing in the first chapter.
What's that?
I said, so we're gonna do
Yeah, do it like we did in the first chapter, exactly. Okay, and you see why, even though it's two inverse operations, they're easy inverse operations the first way. This is one inverse operation, but it's going to be a little on the hairy side, but doable. So let's do it. What's the first thing we're going to do? What do we want to happen first? First entry to be a 1. Okay? Now look at all three of these, and none of them I can reduce to be anything helpful. So let's just deal with that first one. How do we make that entry a 1? Divide by 10. Okay? Now, what's that? Okay, except I'm going to do a little differently. Hopefully it won't be too bad. Okay? I'm going to wipe out these lines. Okay? And rather than putting it in fraction form, I'm going to put it in decimal form. That, at least it looks a little nicer. It might be a pain in the neck to work with, but it looks a little nicer, doesn't it? So that's a 2.3, a 2.1, and a 0.1. Okay? That done, what do we do next? Multiply that new first row by negative 11 and add it to the second row. Okay? That one I can't do just on the same page, so let's just do it. We're using the first row, 1, 2.3, 2.1, 0.1, 0, 0. Let's give our new row. Do second row. Oh, I was going to do that one. No, I'm just kidding. Okay, you do the next one. Yeah, get out your calculator. 11 times 2.3, I believe is going to be should be negative 11 times 2.3, right? That would be 25.3. Okay, when you add them, you also added the 26.
No, I didn't add.
No, oh, you didn't. Okay, sorry. Okay, all right.
Yeah, once you add the 26, it's 0.7.
Yes, 0.7. Okay. Let's do the next one. Negative 11 times 2.1. That's negative 0.9. Okay. Then do the next one. If you use your calculator, I'm going to shoot you. Never mind, I just get it. All right, good deal. Okay. Next one. Please don't. And next. Okay, got it? All right, what's next? Say again? You want a 0 underneath that, and how will you get it? Negative 12 times row 1 plus row 3. So what will that give you? Oh, that was mine, okay? Now you do the next one. Negative 12 times 2.3. Add 27. Negative 0.2. I was going to say it can't be that. 6.2. Okay. Negative 6.2. I'm taking your word for it. You better be right. Okay. Is it that much? Oh, okay. 0.6. Okay. I was going to say. Okay. I'll buy that one. 0.6. Let's see. Negative 0.6. Got it. Okay. I'll buy it now. Okay. Negative 12 times 2.1. Negative 1.2. Okay. And then the next one. Is that right? I know the next one negative 1.2, isn't it? Okay. Both of those were right. And I can do the next one. 1. Okay, good deal. All right. What do we want to happen next? Say again? You want a 1 there. How's the easiest way to get that? You want a 1 in the first non-zero entry in the second row. Now be lazy. You have to think lazy. By the way, I forgot to mark Jonathan when he came in. Perfect attendance. Ding, 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 ding. All week. Perfect attendance. Way to go. Okay. What's the easiest way to do this? You could. That certainly will work. Does anyone see a slightly easier way? What happens if you divide the bottom row rather than this row? This row is going to be a 1 here, 9/7 here, 11/7 there, a 1/7 there, and a 0, which is fine. You know, once you go to the next step, well, let you do that. But what happens if you divided this by negative 0.6? What would you have here? 0. Yeah, more holders. The last one won't be, but the others will be. So let's do that row. So row 3 divided by 0, negative. Why has my pen disappeared? What's that? Yeah, I'm doing row 3. Yeah, and then I'm going to swap them. Yeah, because this is easier to get a 1 there with fewer fractions. And Nigel loves fractions, but the rest of us, we could care less, okay? So divide this by 0. I can't get that to right. This is so frustrating. Okay, No, yeah. 0.6. Okay, so I'm going to have to write it down again, I guess. So this is going to be 1, 2.3, 2.1, 0.1, 0, 0. Now, I'm going to divide, but I'm also going to swap. Okay, so I'm also going to do row 2 and row 3 swap. Okay, so when I divide that row 3, I'm going to move it to row 2, divide it by negative 0.6, and what do you get? 0, 1, 2, 2, keep it going, 0, and then a pain in the neck. A negative 0.6, but I'm also flipping rows. So if you divide, what's that? No, because it's a negative, everything negative. So that's fine. It's what? Yeah. So let's leave that in fractional form, if that's okay. Negative 5/3. Okay. Let's see now. Getting what that is, just to convince myself it's true, that would be 1 over a negative 0.6. Well, first thing I want to do is make that, move the decimal, and that would be a negative 10 over 6, which sure enough is negative 5/3. Okay, good deal. All right, and then we'll have this last row, which is what used to be our second row, a 0, 0. Let's see, I'm going to also do something else. I know Nigel likes decimals too, but, you know, I could go without them, okay, if I needed to, and I think I do. Let's make this a 7. We're also going to multiply this row by 10. 10 times the new row 3, okay. That'll be 0, 7, 9, negative 11, 10, and 0. Huh? I just didn't like messing around with decimals anymore. If I hadn't already changed the bottom, I would have changed it. Yeah, multiply that new third row by 10. That's legal, right? In most states. Okay? All right. Did I do it right? Okay. Next. Okay. Say again. Not yet. You got to get zeros there first. So what's next? Negative 2.3 times row 2 and add it to row 1. Right? Won't that work to make that a 0? All right, let's do it to it then. Okay, middle row stays the same, 0, 1, 2, 2, 0, negative 5/3. We put it left in there just for Nigel's sake. Okay, now, what's the new top row? 1, but I was going to do that one. Next one? No, that's mine too. Okay, now you just start doing. Negative 2.3 times 2 and add it to 2.1. That would be negative 4.6 plus 2.1. Say again? Negative 2.5. Okay? And then we'll do the same thing. That's a negative 2.6 plus 0.1. That's negative 2. Is it? 4.5, yeah. I was going to say it's not 2. Negative 4.5. Okay? Oh, you beat me to it, okay? Uh-oh! Knew this was going to be a pain in the neck. All right. It's a negative 2.3 times negative 5/3. Okay. Ew. All right. So that's going to be a positive 11.5, right, over 3. Let's just leave it that way. In fact, I'm going to make it even worse. 115 over 3. No. 11.5 over 3. I'm going to leave it like that. Sorry. 1.5 over 3. All right. Let's leave it that way for now. Now, what's the next thing we're going to do? What's the next thing we want to happen? Okay, the 7 becomes a 0. How do we get it? Negative 7 times row 2, add it to row 3. All right, let's do it. I can do the first one. I can even do the second one. Okay, I'll let you do the next one. 5, okay? Only it's a negative 5, isn't it? Okay. Next. Woo! Yes. Which one? Okay. Negative 2.3 times negative 5 over 3. Is that what you did? Okay. I've already left that, so let me go back and make sure I'm doing the right thing on it. Negative 2.3 times that. And what did you get, you said? 23 over 6. I believe we're in agreement, aren't we? Because you double the numerator and double the denominator. Okay, I'll buy that because it is easier. And it was a negative, wasn't it? It's positive. Yes, it is positive. 23 over 6. Is that what you said? Good. I like it better. Next, back to reality here. Negative 14 plus negative 11 is negative 25. Next. Uh-oh, I did it. Okay. Next. Let's just leave it as 35 thirds. Is that okay? Okay. 35 thirds. Okay. Now, I need more room. Okay. So move out of this house. No. Okay. Go on. Fiddle with this a bit. All right. Let's go on and erase this row here. I don't think we need it anymore. Don't you see that other way was much easier? Even though it was more inverses, they were easy inverses. Okay? So the point of this is you pay your money and take your choice, but spend wisely. Okay? You've already paid your money. So, all right. What's the next thing we're going to do to that matrix there? Yes, how do we do that? Divide by negative 5. Okay? Can I just do it right here in front of you? What will that be? A 1, a 5, negative 2, negative 7 thirds. You don't need that silly calculator. Okay, right? Yeah. Okay? So, what I'm going to do is erase these and rewrite those. I should have left that. Okay, I just don't want to forget what they are, so I'm going to do it the long way. 1, 5, minus 2, minus 7 thirds. Okay, then I'll erase these underneath. I know that seemed an awkward way to do it, but I just want to make sure I didn't get something wrong. Next. Say that again. Okay. Can we also do row 1? What would that be? 2.5 times row 3 plus row 1. And this was negative 2 times row 3 plus row 2. That's what you said, right? Okay. All right, so let's do that. Let's write down the third row. 0, 0, 1, 5, negative 2, negative 7/3. I'm a little bit bothered. Oh, no, I'm not bothered at all. Okay. Next, top row, what would that be? I can do the first one. I can do the next one. See, that was mine. Okay, next. Ooh, boy. Negative 2.5 times 5. It's going to be 12.5, isn't it? 12.5 minus 2.5 is 10. Is that right? Okay. That wasn't too bad, was it? 2.5 times negative 2 is that right? Am I doing the right one? Yeah. 2.5 times negative 2 is negative 5 plus 0 is negative 5. Now, this one, the one Nozzle's been waiting for. 2.5 times negative 7/3. That's going to be say again? Negative 35 over 6. Watch him do that. Negative 35 over 6 plus 23 over 6 is y'all can do that easily. Huh? Negative 12 over 6, which is? Negative 2, right? Okay. Now let's do that one. That middle row. Okay. I'll do the first one. I'll even do the second one for you. I'll even do the third one for you. Okay? I'll let you pick up from there. I've done too much work for you, okay? What you get? Negative 10 plus 2 is? Negative. Yeah. Say again? Negative 8. Okay? I'm getting lost here. There I am. Okay. Okay. Hey, that was mine. Okay. Next. Say again? No. Y'all do it. Okay. What you get? Say again? 3. 14/3 minus 5/3 is 9/3, which is 3. Is that your inverse of that product? What's that? They have an 8 first. They must have missed it. What did we do wrong? What did you do wrong? Okay. Let's see. Is it this last step? That's the 5. No. 12.5. 12.5 minus 4.5 is 8. Is not 10. What's wrong with you folks, huh? Say again? And got it wrong? Oh, yeah, we went over 1. Sorry about that. Y'all did. Okay. So that's an 8, yeah. Shame on you. Okay. Now, 8, negative 5, negative 2. There it is. Negative 8, 4, 3. 5, negative 2, negative 7/3. Sorry, it's negative 7/3. I had to sneak in there, didn't I? Okay. Now, pretty hairy because when you multiply the two, you got really big numbers and you have to fiddle with them. Okay. But you still got the same answer. The other way was multiplying the two of those, taking inverses of the two of those, which would be a little easier just because because you got leading ones and small numbers. That would be a little easier than multiplying. There you're going to hit your big numbers, but you can handle that, right? So, just want to show you they both work and how important it is to pick the simplest way. All right. One important property in the algebra of real numbers is the cancellation property. That is, let me go to a clean slide here. If you had an equation, AC is equal to BC, how would you solve that equation? These are real numbers. Pretty easy. How would you simplify that equation? Yeah, divide both sides by C, and therefore you divide out the C's and you get A is equal to B. Now, you haven't solved it, but you simplified it, right? All right. Now, invertible matrices have similar, I really don't like the term cancellation properties, okay? So, but let's see what they're talking about. If capital C is an invertible matrix, tell me a few things you know about that C then. Tell me something you know about that C. It's a square matrix. It's got to be invertible. One other thing, which we may not be useful to us now, but the determinant is not zero. Anything other. What's another name for it? Non-singular. Okay. So, we know that about C. They say then, if that's true, these next two properties hold. Number one, if A times C is equal to B times C, then A is equal to B. Okay? Or, number two, if C times A is equal to C times B, then A is equal to B. All right. Now that's what they claim. Notice, nothing is said about A or B being invertible. Okay? Nothing really is said about what sizes A and B are, except they must be the sizes so you can multiply them by C. They don't even have to be square. They could be rectangular. You just got to be able to multiply them by C. What size do you want C to be? You said it had to be square, so pick a dimension. Second? 2 by 2. Easy, really easy. Let's just say n. Keep it really general, n by n. What would A have to be? M by n. Any m, but it has to be the same n. B would also have to be m by n. It can't be different from A, but it has to be m by n. And then you multiply those together, you get those two. There you go. Okay. How about in the second step? What size must A be? Could A be? C, you said was n by n. N by m, any old m, and B would have to be the same size as that picture. So A and B don't have to be invertible, but if C is invertible, then that's true. Now this again is pretty easy to prove. We're assuming that AC is equal to BC, right? And we know C is invertible. So what could we do to both sides? Multiply by the inverse, right? And if you did it to this side, you must also do it to this side, right? What is this? That's the identity matrix. Pretty exciting stuff, isn't it? Okay? And then what's A times the inverse? Identity. A, what's B times the identity? B, bing, 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 bing. Got it. And guess how you do the other one? Except you multiply C inverse in front. Okay? And if you do that, same thing happens. Okay?
So could you do A times C is equal to C times B, switch them around, if they're squared?
Okay, say that one more time.
If A and B are squared, could you do A times C is equal to
B
B, C times B?
times C.
C times B. The C in the front.
C times B.
Yeah, would that work? Or?
Okay. I don't think so. Okay? And now you said A and B both have to be square. Now, same size as C. Okay. But notice you didn't say they had to be invertible. And nothing in the problem said they did. If you because the commutation rule does not work except for invertible matrices, then, and I don't even think it can when you're multiplying two invertible matrices together. Because if you multiply this one by C inverse, then you multiply over here, and that won't necessarily give you the same thing. Or if you multiply here, you'd have to multiply there. So I don't think you could say that. Do not believe you can. There may be some circumstances it would, but in general, no. They have to be what they call right cancellation or left cancellation. Okay? Can't be flipped around. Okay? But good question and conjecture there. I don't see how it could be true, though. Always. Anyway. This is true always for any A and B of the proper sizes. Now, be sure to remember that Theorem 2.10 can be applied only when C is invertible. If C is not invertible, you can't do it, okay? The cancellation is usually not valid. Say usually. You may find some rare exceptions to that, but yet generally not. For instance, example 5 back in section 2.2 gave an example when AC equaled BC, for which A was not equal to B, and the reason for that was C was not invertible in that example. So you can go back and check that out. All right, let's go back to where we kind of almost started, systems of equations. Okay? For square systems, that's the same number of equations as variables, you can use the following theorem to determine whether the system has a unique solution. So this is Theorem 211. A is invertible. And you know what that means, right? Then, if that's given, then the system of equations AX is equal to B. Okay, remember X is your components of your variable vector, and B would be your solution vector. Now, remember when we were doing this before, A could be any size, rectangular, square, or whatever. Now it can't. It has to be square because it's given that it's invertible. So now you have, so your X vector is in components, and the B vector is also in components. Because all it was required for X to be the same number of columns that you have in A, and B would be the number of rows you have in A. But because it's square, they're the same. Okay. Same size, but not the same values. Okay. Now, so this system of equations has a unique solution and that unique solution is X is equal to A inverse B. All right. That's the theorem. And again, it's pretty easy to prove. all you do is multiply both sides by A inverse, because A is invertible, so you know A inverse exists, and basically that gives you the second equation. That's just really ugly at the top, isn't it? Let's see if we can clean that up a little bit. Okay. Because A times A inverse is the identity matrix. So you can leave it off. Okay. So, a needle pulling thread. All right. Let's see if we can get, use the inverse matrix to solve each system. 2x plus 3y plus z is equal to negative 1. 3x plus 3y plus z is equal to 1. 2x plus 4y plus z is equal to negative 2. Okay? Now, it says use the inverse matrix to solve the system. I can hear you now saying, no, it's easier to use row reduction, isn't it? And I'll agree it is. Okay? I absolutely agree with you. But look at B then, and notice what's different about B. Yeah, your solution vector is different, but your matrix is identically the same. And how about C? Yes, the only thing that changes is the B. This is where using the inverse comes to your advantage. Let's say you're a business owner, or you're working at some sort of a problem that linear algebra helps. Okay? You got a bunch of variables, a bunch of constraints, a bunch of conditions, and you're saying, well, what if? What if we shoot for this amount? Well, how about if we shoot for this amount? But all your givens the same. All your equations are the same over here, but what your goal is, that's what you're trying to plan for. What's going to be the best solution that will optimize whatever we're wanting to optimize? If you're going to have to use the same application repeatedly, do the inverse. If it's just a one-shot deal, do row reduction. Row reduction is easier once. But if you have to do the same matrix and do different things, you have to go through all the row reductions again to get it. So why? Let's just do it once. So it says use inverse. So how would you proceed? Say again? Put it in a matrix. And what would that matrix be? 2. All right. Now, we're not worrying about the solution part. If we're doing Gauss-Jordan row reduction, we would worry about that. We're not worrying about it now. We want the inverse of that matrix. How would you get it? Yeah, you've got to augment, wait, or adjoin the identity matrix to it. So let's do it. And that would be? All right, good deal. Now, what a pain in the neck, isn't it? Isn't it just miserable? Okay. What would be your approach? Okay, I like that. This one, dividing by 2, is going to give you a whole number, half. Not bad. The top one, dividing by 2, is a whole number, fraction. And Nigel likes that, right? Okay. The next one is whole number, fraction, fraction. But guess what? Those fractions are, not as easy as 1/2, okay? Those are repeating decimals, this is a terminating decimal. So I like the idea, and let's do them both at once, okay? Okay, so I'm going to move the row 3 to row 1 and divide by 2. So 1, 2, oh, he likes his decimals now, huh? 0, 0, 0.5. Okay, we'll see if that works for us. Okay, second row stays the same, 3, 3, 1, 0, 1, 0. Okay, third row becomes 'Did I get it right? Good deal. Next, let's see. Let me write down what we did. Row 3 over 2 is exchanged with row 1. You could have written that here or there. I don't care. Okay. We did it. Next. Say again. I need a 0 instead of a 3. How do we make that happen? -3, 1 plus row 2, and then we'll want a 0 under that. How will we make that happen? -2 row 1 plus row 3. Okay, let's do those in some order here. I'm going to write down the first row. 1, 2, 0.5, 0, 0.5. I'm running out of time, so I'm trying to hurry up. Next. -0. -3, isn't it? Okay. Okay. Second? Okay. -0.5. Okay. You could do it a couple ways. I said -3 halves plus 2 halves is -1/2. Got it. Next, I can do that. Ah, you beat me to it. Okay. -1.5. Okay. Next. Oops, that was mine. -1, right? Okay. 0, right? Is it? 1, okay. Okay, that was my 0, okay. Say again? -1? Yeah. Okay. What you want next? Say again? Yeah, swap and negate, right? You're getting the idea, you lazy bum. Okay. So this would be row 2 exchanges with negative row 3 or something like that. Okay. So I'm going to leave row 1 alone for now. 1, 2.5, 0, 0.5. And my new row 2 will be 0. Say again. 1, right? 0, -1, 0, 1. All right, the third row will be 0, -3, -0.5, 0, 1, -1.5. Okay. Does it bother you or shifting the rows around? Could this possibly come out being at the inverse? Yeah, all these are legal maneuvers. Don't sweat it. It'll happen. What's next? Say again. 0 above and below that 1. So how do we get that to happen? -2, row 2 plus row 1. And we'll also do 3 row 2 plus row 3. Okay, so let's do the first of those. See if we can scrunch them in here. I'm going to write down the middle row, 0, 1, 0, negative 1, 0, 1. That, I like the looks of that, okay? Next. 1, 0, you're too fast, okay? 0.5. Say again, 2, 0. Say again. Negative 1.5. Next. I got it. 0. I got it. 0. Negative 0.5. Say again. 2. 3. Okay. Only it's negative 3, isn't it? Is it? Okay. I got it. What's the last one? Oh boy. 1.5. Oh, calculators are moving slow today, aren't they? Okay. Now, what you want to happen next? Okay, you want that negative 0.5 to become a 1. How do we make that happen? Or multiply by negative 2. That would work, wouldn't it? Is it a little easier? You like dividing by decimals another. Okay. Let's multiply. Okay. All right. Good. Lazy move here. He's going to add these two rows together before we change that. Notice what happens there? You don't have to go back. So sure enough, that top row becomes, we'll do row 1 plus row 3 before we change row 3. That's legal in most states. So what do we have? 1, 0. I can handle it. 0. Say again. One more time. Negative 1. Okay. 1, 0. All right. And we'll leave second row alone. 0, 1, 0, negative 1, 0, 1. And then what's that new third row? We're going to do negative 2 times row 3. So that will become, I got the first one. I've got the next one. What's the next one? Negative times negative. Positive 1. Better be. Next. 6. Next. Negative 2. Next. Say again. Negative 3. Is that what I heard? Okay. There is the inverse. Whew. We haven't solved the first equation yet. But what do? We multiply that inverse. And which side? I think this side is right. Times your negative 1, 1, negative 2. 3 by 1. Okay? Blank, blank, blank. Right? And what fills in the blank? 2. Next. 1. Yeah. Negative 1. Negative 2. Is that what you said? Okay. 2, negative 1. Okay? So the solution there is x equal 2, y is equal negative 1, z is equal negative 2. Okay? Now, if you did row reduction to get that next one, then what you would do is have to do all your operations again. Not as many, not as hard, but you do it. But now we can use that same matrix, negative 1, 1, 0, the inverse matrix, -1, 0, 1, 6, -2, -3, and multiplied by the b part is 4, 6, 8, no, 4, 8, 5, I can't read. 4, 8, 5, okay. And that's not too hard to do, is it? Again, a 3 by 1, what would that be? 4, 1, -7, is that what you said? Okay, I didn't keep up with you. Is it in the book or you? Yeah, you're really quick. Okay, good. All right, good deal. And then that last one, it's the 0, 0, 0 there. Ah, he's really lazy without doing much work at all. Now, what does that tell you? It tells you that the one and only one solution there. Normally with those homogeneous equations, we expect maybe to have the trivial solution and then maybe infinite number of others. But in this case, because that has an inverse, the trivial is the only possible thing. So once you got the inverse, then it's easy to do that multiplication. Doing it the other way, you'd have done row reduction on all three over and over again, doing the same reductions, but because that constant vector is different every time, you have to do it all the steps all the way through. This way you do them once and then just do the multiplication. So I don't know. Because that one had that 0, 0 at the end, I think it would have still been easier to do 2 by row reduction than do 1. But if you had 3 or 4, no question, inverse matrix is the way to go. We did finish chapter 2.3, section 2.3. Homework exercises. Now remember, odd number exercises have answers in the back, but they also have worked out solutions at calccheck.com. So any of the odds 1 through 5, any of the odds 7 through 29. If 27, 29 get too hairy for you, you can leave those off, but look at them anyway. Any of the odds 31 to 35, do either 37 or 39 or both, that's up to you. Either 41 or 43 or both, that's up to you. Either 45 or 47 or both. Either 49 or 51 or both, you. 53, 55, 57, 59, 61, and then the rest of them I'll let you decide any of those odds you want to play around with. I would look at something, anything that might lead you to a paper topic. There is something called a householder matrix. I don't know if that's named after somebody. That's a really weird name, or if it's some other reason for doing that. But that's something I'd look at anyway just to see because it's interesting. We'll begin next time in 2.4. Any questions? Okay, please get me some work sometime next week, either end of this week or sometime next week. We'll see you Monday. Have a good weekend. Well, I'll see all of you again today.